Hi there, this is Matt Heffernan, and welcome back to my channel. This is another episode of Slithy Vlogs, number 18 we're up to now. And the last 4 episodes of Slithy Vlogs, of course, have been dedicated to what has been called and embraced by the community as the 8-bit Battle Royale, where I've been taking different 8-bit computers from the classic 8-bit era and having each of them generate a Mandelbrot set fractal using the standard algorithm that is described in the Wikipedia article for Mandelbrot set. And it's not a terribly clever algorithm. It's a very brute force affair. And so I made a version of that in just standard basic, and then put in some of the window dressing required of all of these different platforms in order to get that fractal generated for each of them. And of course, you have different levels of capability in terms of how much resolution you have, what your color depth is. And of course, those 8-bit computers were fairly lacking on both counts. So what I came up with for that was the lowest common denominator, at least of the systems that I was primarily concerned with, was of course, the classic Sinclair ZX Spectrum, which gives you a 32 by 24 and 15 colors that can be, you can set any of those character spaces, the 32 by 24 spaces, into whatever pair of colors you want. And of course, we were just doing a solid color, so and you have 15 different colors to choose from. So that's where we came up with how we were doing that, and that was a pretty good standard to reach for a lot of classic 8-bit micros, but for the Commander X16, we're dealing with a much more capable machine. And so now we're going to see what the actual performance is of this platform when we start pushing it graphically. Now, to recap what we saw before, using this dumbed down, extremely low res, low color depth version of 32 by 22, of course, because the ZX Spectrum is always going to cannibalize those bottom 2 rows of characters. So 32 by 22, and then going up to 15 maximum iterations because the ZX Spectrum only has 15 unique colors. And by doing it like that, just placing those constraints on the Commander X16, of course, those constraints are not reasonable. Obviously, you can do much better, but by placing those constraints, it can perform extremely well. It does it in basic in 23 seconds. And then I did an 8.8 fixed point implementation in assembly language, so you have 16 bits for each value, and it could do that in 3.2 seconds. So very fast in terms of fractal generation, but these were very low-res fractals. So the Commander X16 has 640 by 480 graphics, and it also supports 256 colors, but because you only have 128K of video RAM, it doesn't support both at the same time. But it does 320 by 240 bitmaps at a solid 256 colors, no problem. So that's what we're going to hit for. That's what we really want to be able to do, is do that 320 by 240 plot of a fractal Mandelbrot set. But because we have a full 256 color palette, we can do more than just 15 iterations. And what I've seen dealing with this resolution in particular is 48 iterations seems to be about the sweet spot. You go more than that, you're not getting a whole lot more information in your plot. And you go less than that, and it's a little lackluster. But 48 seems to be about where you want to be at 320 by 240. So we're going to basically do the same basic program, except we're going to be expanding the numbers for it. Instead of 32 by 22, it's going to be 320 by 240, and instead of up to 15 iterations, up to 48 maximum iterations. So all that's pretty much the same, except that instead of dealing with setting whole characters to a particular color, it is setting individual pixels to a specific color. So for assembly, the 8.8 fixed point representation for numbers, it's just not going to cut it because we're dealing with 320 by 240. It's above 127, so we really need more than 8 bits for the integer part of our number. And by just doing 16 bits, obviously that's overkill at that point. We really only need like 10 bits for the integer, and keeping it with 8 bits for the fraction. We could get a little more accuracy if we shifted that all up and did, say, a 10.14 or something like that, where we got really precise. But again, 320 by 240, it's not a lot of resolution, really, when you're talking about a fractal plot. The classic dorm room fractal poster is going to be much higher resolution than that. Nobody's putting up a 320 by 240 poster. So let's take a look at what that is going to require for our programs. Of course, like we said before with BASIC, it's very simple, very similar to what we had before. But what you will notice here is the appearance of some pokes up at the top. So what these pokes are doing is setting up the layer configuration for the Vera display adapter to have just layer 0 be the bitmap that we're going to do, and then disabling layer 1, which has the text. So we don't need to see any of the text down there. We can just disable it, and we'll do everything we need to do in something outside of layer 1. And we could bring that back later on, but as we'll see, that's not going to quite work, because what we're actually going to do is overwrite a big chunk of VRAM, including where the character glyphs are defined. So anyway, at the beginning, we set up these pokes, we get the layer configuration set up, then the rest of it, very simple, extremely the same as to what we've done before, except here you can see the pixel X and Y loop indexes are going to much higher values, and of course then we are scaling down the little axes quanta to what we need. And also you'll notice is that the range that we're doing for Y is actually being expanded by a bit, because what we want to have are actual square pixels that make sense, so that the Y and X displacement of each pixel are the same. And that way, this nice round cardioid that's in the middle of the fractal is nice and round and not sort of stretched out like we kind of saw with some of the others. But it didn't really matter. It was so low resolution. But now we're going to get past that point of the sort of fractal uncanny valley where we want to see it look a little more realistic, a little more orthogonal to what we're expecting. So then we can see down here, after the normal calculation bit, is taking the number of iterations we go through, and then we're adding 80 to it. And what that does is gets us up into an aesthetically pleasing part of the default palette, where we go from like shades of yellow into shades of green, and it starts to, again, look more like a real fractal plot by using this particular part of the palette. And of course, we're dealing with up to 48 iterations. So if we get up to the maximum number of iterations, which would be 48, and then I would end up being 128. And in that case, for maximum iterations, we want to then pick color 0, which is black. So we get a nice black interior. So definitely a much nicer looking plot is what we're going to be getting out of this. And then we got to do some business here where we set up what our VPoke is going to be, how we're going to start putting these pixels into VRAM. And by default, we're assuming we're in bank 0, so that first 64K of VRAM, and then we're starting it at hex 4000, which puts it after the bitmap for layer 1, which we've of course made invisible, but we're not overwriting that with this. and then saying, well, y is going to be the pixel y. And if if y is less than 153, we know we're in that first bank, so we're not going to change those. But if y is at 153 and the x coordinate is less 192, we're still on that bank 0. It's at that at row 153 at pixel 192 of that row is where the bank switch happens when you have the bitmap start at hex 4000. The math all works out. Trust me, you can check it on your calculator if you really want to see it. And but then if we get past that if statement, then we set up for bank 1, and then our offset is going to be just subtracting that 192 for the x, and then subtracting 153 from the y, and then when we do the vpoke, all the math will work out so that we're just doing one pixel after the other. And that's it. That's how the basic part works. Now, to do this in assembly, there's a lot of things that we can do to make this much, much faster. And of course, the big thing is the math. Like I said before, instead of doing 24-bit floating point, which is the default for Commodore BASIC, what we can do is a 24-bit fixed point implementation, and making it even more simpler by having it 16 bits for the integer and 8 bits for the fraction. Gets us 256th resolution, which is close enough for government work right here. This is not government work. This is purely private sector, but you know what I'm talking about. So up here now we can see things are a little different from the standard 8.8 library, where we can see that each of our meta registers are now taking up 3 bytes on the 0 page. And then we have all the same sorts of macros. Some of them are a little different, where now we can take, say, an integer value. That value could actually be 16 bits wide. So we're setting that then here at like the +1 and +2, and zeroing out the low byte, so that's a 0 fraction. Just doing a lot of stuff like that, and just taking into account how much bigger these numbers can possibly be. So we take this library, this fixed point 24, and we include it in now Mandelbrot 24. And here we can see the those new bounds that we defined before, but now our constants are 24-bit constants. So minus 2.5 is now FD80 instead of just FD80. And then 3.5 is 000380 instead of just 0380 for 3.5. And then, of course, we also have the expanded range of the y-axis, so that we're still having a nice square plot. And, of course, then we are setting up our width of 320 by 240 and 48 iterations, and we're off to the races. All of our variables need to be D words instead of words, so we're taking up more space than we need. It doesn't matter. But then once we actually get down to the algorithm itself, it's mostly the same, because we're still using a lot of the same macro names, and we just have to sort of tweak it a little bit. Instead of some of the subroutines that we had in the old version, we've replaced those with macros in here. And you can see all this. You go to the repo, you can see how the code works. And then here in the main assembly language program, we are including that Mandelbrot 24 implementation, defining all of our registers, the ones that we poked before, and then the ones that we need to do a vpoke, which of course are these guys right here. The rest of them we've kind of did already, except for the H scale and V scale, which we did by doing a screen 0 before, like we can see here in basic. Screen 0 gets us to that 320 by 240 mode, but instead what we're going to do here for DC H scale and V scale is writing 64 to that, which will do effectively the same thing. But then here we can see those same pokes that we were doing to Vera registers before, and we're setting up that layer 0. And of course, we're also disabling interrupts for this whole deal. And then instead of having to do all of this math for determining what our vpoke address is going to be, what bank and address within that bank we're going to do, we can simplify that much more in assembly language by just getting our data port 0 set up. So we're storing 0 in a Vera control, it's saying data port 0. We're doing a stride of 1, and then using this VRAM bitmap that we defined. Again, sticking at 4000 hex. And VRAM bitmap is what's going to be the first address that we start writing to, and every time we write to data port 0, it will increment the address register automatically. And so all we got to do is just keep writing new color indices to it, because we're doing a 8-bit per pixel bitmap, as we can see here. And of course, we are using that same bitmap address for tile base to say here's where that bitmap actually exists. So it all works together very easily, comes together. That configuration is very easy to make happen. And then we just get to the regular loop. Of course, our loop indices need to be 2 bytes wide, so that adds a little bit of extra code. But then once we get to the point where we're ready to call mandget, we're all set there. Instead of using the X and Y registers, of course, we're just using this mandX and mandY variables that need to be set. And then we do the same thing we did in BASIC, where we're adding 80 and seeing if we're 128. And if we are setting it to 0. And then we just write the pixel. And to write the pixel, it's a single instruction, just storing that iteration value that's been offset by 80 to data port 0, and we know that it's going to be at the pixel that we want to write, and we can just keep writing to it, and each pixel will come in order. So it'll all work out because we're making sure that in our loop we are going through the X's and the Y's in the correct order. So doing each row, so Y0 going through all the X's, and then Y1 going through all the X's from 0 up to 319, and it all works out in the end. And then, so after we write the pixel, we're dealing with the end of the loop, and so having to deal with all of the checks and everything that you need to do these 16-bit loop indices. So it's a little more fussiness at the end, but these are all very quick instructions. And then finally, once we fall out of the big loop, we re-enable interrupts and we return, and everything is good to go. So now let's see how fast these different implementations of this algorithm can work. So in one corner, we have BASIC. There's the whole BASIC program. And in the other corner, we do a list, and it's the machine language program. Everything's all compiled, ready to go. And I've got a stopwatch up here. So this stopwatch, it will let me record when the first one to complete, which, spoiler alert, it's going to be the assembly version. We'll be able to record when that completes, and then keep going and see how much longer it takes for the BASIC version to run. So we're going to be real nice, and we're going to give BASIC a head start, and start right here. There we go. See, we gave BASIC like a second and a half or so. And here, we're not going to be that nice. So let's start running the assembly language. And now we can see already that the assembly language one is running much, much faster. Of course, this is the easy part. It's not doing a lot of iterations. We've just gotten to the point where we're getting up to more than like 4 iterations. And you can already see that top extension of the fractal where it's getting into those higher iterations, and how much nicer it's already looking. We can see we're going from this yellow gradient into these green gradients, and yeah, it's starting to look like a real fractal. So we're going to just time lapse this. We're going to let the assembly language version just run to completion, and we'll record that time and see how quickly this happens. All right, let's go. All right, we're coming here to the end, and we're going to record where it hits, and boom. So 12 minutes and 17 seconds. Not too bad. Of course, we could shave a couple off there because we were about 2 seconds in. And yeah, we'll see where we end up with the basic one. As you can see, it's still only about a third of the way down. But of course, you'll see here the plot on the right. That middle third is really going to take up most of the time of the total generation. So it's definitely going to take way more than 3 times what the assembly language version did to do everything. So let's see how long this actually takes. We're going to fast forward again. Getting to the bottom here. This should go pretty quick. Just a little one iteration part. And last row. Ah, 1 hour and 12 minutes. So definitely a lot longer. We're talking about 6 times longer to do it with basic. And yeah, it is definitely very interesting. We get a much more aesthetically pleasing look. And yeah, I think we are getting somewhere. So I think we'll try this approach maybe with some other systems, and especially ones like the Commander X16 that can do these more colorful displays. But until then, if you want to find out when the next episode is coming out, the easiest way to do is to subscribe to the channel and then click the bell to be notified, and you'll be able to see these videos as soon as they go live. Now, for this next one, instead of coming next week as normal, I'm going to be taking a bit of time off from the channel. Got some other stuff going on, and it's going to be a little more sporadic this October, or rather this September, and then starting going back to normal in October. But of course, if even in those circumstances, you can still get a even sooner notification of new videos and watch them before anybody else if you just join up on Patreon like these folks here, and really have a say in what happens on the channel, and get a lot of good inside information, and have a lot of really good discussions about things that go a bit beyond what we see in public. All right. Well, I hope you enjoyed this, and I will see you again soon. Bye-bye.